In this video, we are going to determine the specific heat capacity of the unknown sample. The question says, an aluminum calorimeter with mass 100 grams contains 250 grams of water. The calorimeter and water are in thermal equilibrium at 10 degrees Celsius. Two metallic blocks are placed into the water. One is 50 grams piece of copper at 80 degrees Celsius. The other block has mass of 70 grams and is originally at a temperature of 100 degrees Celsius. The system stabilizes at a final temperature of 20 degrees. Determine the specific heat capacity of the. So here the data that we've been given is the mass of aluminum calorimeter, which is 100 grams, and the mass of water in the calorimeter is 250 grams. Both the aluminum calorimeter and water are at 10 degrees Celsius. And then the mass of copper is 50 grams at 80 degrees Celsius. The mass of substance X is 70 grams at 100 degrees Celsius. Then the final temperature of the system is 20 degrees Celsius. Now, based on this information that we've been given, we're going to determine the specific heat of the substance that we do not know. So the substance that we don't know is substance X here. So in this case, we're going to consider the aspect of energy conservation. As we work out this question, we need to understand that the summation of the energy must give us 0 because energy can neither be created nor destroyed. But before that, before we come to the expressions that are going to lead us to find the answer, which is the specific heat capacity of substance X, we need to consider some of the standard values of which the specific heat capacity of water is this, then for aluminum is this, and for copper is this. Now, let's proceed. So, we know that from the principle of energy conservation, as I said, the energy that is going to be gained by water and the calorimeter must be equal to the energy that is going to be lost by copper and substance X. So we are going to, if we add all the energies, we must get a 0. So the energy by calorimeter plus the energy by water plus the energy by copper plus the energy by substance X, this must give us a 0. Now, we know that heat energy is calculated by using the formula energy is equal to mc delta T, where m is the mass, then c is the specific heat capacity of a substance, and delta T is the change in temperature. So here, we are going to indicate for all these quantities that have been given here. So the specific heat capacity of the aluminum calorimeter, we are going to have, so the mass of the aluminum calorimeter times the specific heat capacity of aluminum calorimeter times delta T plus the mass of water, C of water, delta T plus the mass of copper, C of copper times dt plus the mass of substance X times the mass of X times Cx then dt. This must give us a 0. So from here, since water and aluminum calorimeter have the same initial temperature, we can in fact even add them together so that M aluminum, C aluminum calorimeter plus M water, C water, delta T. Okay, since they are common, so we can even see MCU, which is the mass for copper, then the specific heat capacity of copper dt is equal to then the negative of mxcx dt. So that from here we can even make substance X, or rather the specific heat capacity of substance X, the subject of the formula, by simply dividing by negative mx, the mass of substance X, and the change in temperature. Even here, negative mx dt, or change in t, so that this and this will cancel, this and this will cancel, and the negative and negative will cancel. And what we're going to have is Cx is equal to, so what we're going to have is the mass of aluminium, C of aluminium, plus mass water, C water, plus mass of copper, C of copper, delta T over negative MC, sorry, negative mx dt. So now, plugging in the values, we are going to have the mass of aluminium. If we convert that to, that is the mass of aluminium given is 100 grams, which is just 0.1 in terms of kilograms, times the specific heat capacity of copper, which is, or aluminium, sorry, aluminium, which is 900 joules per kg per degree Celsius, then times the change, okay, or plus the mass of water, which is 250, which is just 0.2, okay, 25 kg, times the specific heat capacity, which is 0.186 grams per kg per degree Celsius. Then the change in temperature, which is that we have 20 minus 10. So we have plus the mass of copper, which is 50, which is just 0.05 kg, times the specific heat capacity of water, which is, or copper, which is 387 joules per kg per degree Celsius. Then the change in temperature is 20 minus 80. So degrees Celsius, degrees Celsius. Even here we have degrees Celsius, degrees Celsius. So here, so all these we divide by the mass of, okay, so the mass of X, which is 70, which is 0.07 kg, times the change in temperature, which is the final temperature, which is 20 minus 100 degrees Celsius, degrees Celsius. So from here, what we're going to have is, so this part, if we punch on a calculator, what we're going to have is 1.02 times 10 to the power 4 joules. Okay, so the kgs and the kgs are going to cancel. What we're going to have, so here, what we're going to have is this kg and this will cancel, even this and this will also cancel. Then this and this, okay, the temperatures, the units for temperatures will also cancel. We're going to have this side will just be joules, and this will be over, okay, since we are just dividing. This times this, what I'm going to have here is 80 times 0.07. What I'm going to have is 5.60 kg degrees Celsius. So this is our Cx. So Cx, which will give us this will give us this into this. We're going to have 1.82 times 10 to the power 3 joules per kg per degree Celsius. So this is the value for the substance X. Thank you so much for watching the video.